October-November 2020, Paper 2, Variant 2. Question 1. Atoms contain subparticles like electron, proton, neutron. Part A. The diagram shows behavior of separate beams of electrons, proton in the electric field. Part 1. Complete the diagram with the relative charge on the plate. Okay, so we know that electron is negative charge, it will attract to positive charge plate. So here is positive. And proton is positive charge, it will attract to the negative charge plate. So here is negative. Part 2. On the diagram, draw a line to show how the separate beams of neutron from the same source behave in the same electric field. So neutron will not affected by these charge plates, so you just go straight. You just draw straight line, okay, for the neutrons. For part B, first you need to get the electron configuration. You can deduce it from the periodic table. So it's 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, and 4p6. The question asks, state the numbers of occupied orbitals in the isolated atom of krypton. And the type of orbitals, they are SPD, the occupied spt orbitals. Okay, so first you need to know the s subshell is actually the s orbital itself. Means this s subshell means the s orbital itself. And the p subshell, in the p subshell, it has 3 orbitals. So means, for example, this 2p subshell, in there it has 3 orbitals. And the d subshell, it has 5 orbitals, like this 3d. In there, this subshell, it has 5 orbitals. Okay, if you understand this, then you will know how to do. Okay, the numbers of occupied s orbital. So we have 1, 2, 3, 4. So here. The numbers of occupied p orbitals. So now we have this, and this. So there are 3 subshells together, and 3 subshell we know that is 3 times inside the p subshell it has 3 orbital, so it's 3 times the p subshell, so it's 3 times 3. So total is 9 occupied orbitals there. So means these 3 together, this, and this. Okay, there are 9 orbitals in there. For the occupied d orbitals, so we know that only 3d subshells involved, and this 3d subshell in there it has 5 orbitals. So that's why answer is 5 here. So it's 4, 9, 5, okay, orbitals. Part 2. Complete the diagram to show the numbers of relative energies of electrons in the silicon. So first you need to find the electron configuration for silicon. It's 1s2, 2s2, 2p6, 3s2, 3p2. Okay, so you just fill up the orbital diagram, follow the rules. It must from lower energy level to higher energy level. And after that, it has to fill singly first, means the hundreds. Okay, so first two electrons in the s orbital. Okay, so 2s2, 2p6, 3s2, and 3p2. So the 3p2, it must go from left to right. First one, second. It must fill singly first, then it's pair. This is the hundreds. Okay, so therefore you must follow this drawing. Okay, part 3. The diagram shows a type of orbital. This one is 2 lobes, so it's the p orbital. State the total numbers of electrons that exist in all orbitals in this type, okay, in the atom of fluorine. Fluorine, we know that, okay, it has 5 electrons in the p orbital. 1s2, 2s2, 2p5. So therefore, total numbers of electrons in this p orbital is 5. Part 4. The first ionization energy of the elements in the first row of D block, from the scandium to copper, they are very, very similar. Okay, for all these elements, it is 4s electrons that lost during the first ionization energy. So it's always the 4s electrons removed first. Suggests why the first ionization energy for these elements is very similar. In order to answer this, first you need to understand how the thing works. Okay, I choose 2 elements, titanium and the iron. Titanium first, followed by, of course, later for iron. Not really direct follow, it's just the same row, but the iron has more electrons or more protons and electrons. Okay, for titanium, we know that is the argon 3d24s2. Okay, the 3d orbitals will be lower than 4s when the d orbitals has electron. That's why it's look like this. Okay, this energies diagram, this orbitals diagram. Titanium, the 3d2, the 2 electrons, okay, is filled in the d orbital, singly filled. And if now the electrons try to add to the elements, or the electrons number increases, so the electron will actually add to the 3d but not 4s, because 4s already filled up. So means the elements that after this titanium, okay, or iron later, so the electrons will fill into 3d orbitals. And these 3d orbitals is actually the inner shell. Means when across this row, this from scandium to the copper, all the electrons actually they added into the 3d, things like this. When electrons add into the inner shell, it will give more shielding. So we know that shielding is the one that overweight the nuclear charge or nuclear attraction. The higher the shielding, the attraction of nucleus is weaker. That's why when it's across this row, even though proton number increase, the IE will not increase so much, or the IE is almost similar, because when proton increase, the shielding also increase, because electron added into the inner shell. That's the reason why it's always constant, right? So if you understand what I telling you, so this statement you should be able to understand. Across the D block, nuclear charge increases, the proton increase means. However, the electrons are added in the 3D subshell, which is the inner shell, and it will increase the shielding. Shielding to what? To the 4s electron, then it will be easier for it to release because of the shielding. Therefore, they have the similar nuclear charge, okay, for the nuclear attraction for the outer electrons. Means it's almost constant for the first IE. Okay, part C. Hydron is a general term used to represent these ions. State in terms of subatomic particle. Subatomic particles means protons, neutrons, electrons. Okay, what is the same about each of these ions and what is the difference? Very easy. Since they are the same elements or they are isotopes, so they must have the same proton number, and it's just the mass or the neutron number difference, right? Okay, that's all for this question. Thank you.